Thank you everyone for coming this afternoon, and it's my great honor and pleasure to be here. And this is my first time being at KAST, but the second time in the Jeju Island. It's a beautiful island actually. So I was just here like about 20 days ago at IEEE AI IV conference. Since I saw that the topic of this session is AI connects all, and and I know this is hosted by KAIST and Ijo University colleagues. Actually, I had before I joined this event. Actually, I had some interactions with both university, like KAIST folks. We actually invited them to have workshops and data exchanges. And for Ijo University and their president also came to our university for some collaboration discussions. So yeah, it's a great opportunity to get reunited with this great community and share some of the thoughts and our work. So I'm going to talk about some of our work on connected automated vehicles and also how we can benefit from the recent booming technologies and developments in the space of AI. And I'll just briefly discuss my thoughts about which areas what kind of AIs and also how we spin and package the AI for the use of transportation. So I think I had flicker. All right, let me see. Oh, sorry. All right, yes, I need some time to exercise how to use this clicker. So as you know, that connected automated vehicles, you saw some studies in the last century, in the 1990s, right? They have made bold predictions about what connected vehicles or CAVs could help us. I'll put a timer here. So basically, people predict that automatic vehicles can improve safety, mobility, and energy efficiency dramatically. Reducing 90% of the crashes, multiplying the capacities, improving energy efficiency over 50%, right? So, and if you look back then in 1997, this technology had already been piloted and demonstrated along a closed-track test road, and you see these Platinum vehicles follow each other very closely, and I calculate their head weights like 0.5 seconds or so, or even less than that. So with that, you could almost quadruple the transportation roadway capacity, right? That's quite impressive. And back then, if you speculate what the future would be like, one of the pictures could be like this. All right, so all these road users are harmoniously passing the intersections autonomously. Although I would be scared walking across the intersection, but this is a computer graphics, no worries, it's just the copy pasting the same users. But it shows the idea about what the future would be, right? So let's just fast forward about almost 30 years and see where we are at now, right? We have some companies that have some of the deployed and the commercialized autonomous vehicle technologies for passenger cars and also for other modes of transportations like bus, right? This kind of shuttle buses, and I heard you want to make your. I actually had a tour at the lab, and I saw some small electric vehicles, and you want to make KAIST want to make them connected first, and maybe in future it can be automated. And then you're going to see lots of automation commercial companies for trucks, for delivery vehicles, and even in the restaurant you're going to see this kind of delivery robots, right? So there is lots of commercializations going on, and one of the key technologies in the road vehicles is actually, it's probably called adaptive cruise control, and that technology supported lots of low-level production automated vehicles, right? So when you say autonomous vehicles, you may think that this is a future concept, but according to the SAE definition, level 1 and level 2, those low-level automations are everywhere across the world. Like in the US, like 92% of the new cars have adaptive cruise control, which is level 1 automation, and 50% of new cars have lidar and lane control. Of course, among the new cars, that's level 2 automations. All right. So and the key technology, which is the ACC, have been equipped in lots of cars. How many of you have level 1 or level 2 automation in your car? All right, I see quite a few hands, right? So, yeah, we're right. It's almost everywhere. Not everybody has it, but you'll see them pretty frequently. So if you have an ACC vehicle, you're going to see like you can set the speed and headways like this, and also you may be able to adjust the headway like one, two, three, 4 levels. This is for our lab vehicles. Some vehicles have 3 levels or so. So you'll be able to adjust them and set up an ideal following distance. Then the vehicles, if the vehicle drives on the freeway without signals, it will just automatically follow the preceding vehicle, right? That's a technology we know. So with this kind of technologies, what we can think about the new opportunities and challenges we have. Particularly along in conjunction with AI technologies. I think the first thing we want to think about would be vehicles as a sensor. So basically every vehicle right now, new vehicles has equipped with lots of sensors, mostly cameras, and some have radar and also lidar, right? All these vehicles can perceive the surrounding environment in real time, and actually you can merge such information together to get the holistic picture about the driving environment. And the video I showed was actually reported by Tesla. They shared their development about using actual vehicles as sensors. Here you see actually the vehicle can perceive its environment and sort of generate a map as well as road users' vehicles. And they can also put together multiple vehicles and really construct the holistic view, real-time view of the whole network, right? So maybe people may also say this is cooperative perception. So this gives us tremendous opportunity about real-time information retrieval as well as management, right? And also, given that the rise of these automated vehicles, we want to check against our original, goals and objectives. Like I said, don't forget the history. All right, 30 years ago, we want to have this technology such dramatically improve the transportation system. Are we there? And how are we going to check against them? For along different performance measures such as safety, mobility, energy, and climate changes. Oh, sorry. Also, the development of technology really gives our community, transportation field, unprecedented opportunities to be innovative, to create the technologies ourselves, right? So, in the past, the civil engineering, particularly transportation, focuses more on the infrastructure. As now, it looks like there is a trend of intersecting the automotive engineering with transportation engineering. That gives us opportunities to create new technologies, such as cooperative driving automation, to make the vehicles not only automated but cooperative with each other and with the infrastructure units, and to form connected automated transportation system. So there will be lots of opportunities as well. So how to capture, grab, and capitalize on these opportunities? I think artificial intelligence or AI methods just came in the right time. So the changes, as Dr. Huang mentioned this morning, we have big data, right? Before, we had lots of studies that just focused on very simple first-order models. We look at the two cars and look at how they follow each other in ideal one lane, or you add multiple lane, you think about the car following, that kind, or lane changing, that kind of simple models. We've been enjoying doing that. But right now, as the data comes, you have lots of more high-resolution data, and the problem gets a lot more high-dimensional. And you can you can really dig into the detail of high nonlinearity of this system. Even the behavior side of a single vehicle, of a platoon of vehicle, or the transportation systems. The data comes in more diverse and more detailed formats. Like in 20 years ago, maybe we have just the aggregated data, flow count, density, that kind of thing. Right now, we can have holistic telematics data of vehicle trajectories and all their functions, like steering wheel maneuvers, pedal maneuvers, and their positions, all these things. And also, you can have that information for multimodal users, including vulnerable road users. Actually, my colleague Sky Chen, he's actually been working on lots of this data and vulnerable road user related projects, and he's also working on active on AI as well, collaborating with Wisconsin Department of Transportation. So I'm going to talk about how do we capitalize on these opportunities along the challenges and opportunities with AI from these three aspects. First is perception, and then I'm going to talk about evaluation and cooperation. So the perception is just the idea I mentioned, the vehicles as a sensor. So most of the recent production vehicles have equipped sensors, right? As I mentioned, there's all sorts of sensors like video cameras, right? And some of the newer technologies, particular cars manufactured in Asia, also tried the LiDAR in their, actually, like Xiaomi, I think they also had LiDAR equipped in their car, in their smart car to drive their autopilot, right? And these are some of the cameras are just like this, and LiDAR and radar and some other things, actually. So basically, with this technology, just as I showed in the video from Tesla, right? You could assemble the sensors from roadside, ground, and air vehicles from all these, different units to actually fuse them and get a comprehensive picture of what the roadway environment will be. With that, you can have real-time detection of road users. And on top of that, if you bring back the data and do some offline process, you could have some static digital twin of infrastructure geometries. You can do a lot of things like asset management, payment condition management, right? Inspection, like that. So you're going to have near real-time detection of the road conditions. And also you can have more real-time inspection of the road users, right? And, like the road conditions doesn't change a lot over the time, but the vehicles are moving a lot. You have a lot of these things are real-time, so you could use all these videos from different parties, different entities to inspect the environment and get useful information. For example, we actually worked with Federal Highway Administration as well as Argonne National Lab and also some other partners. Here, some of the fun project we had was using the air vehicles. Like this is a helicopter. It has 3 8K cameras actually. It was used to shoot Hollywood movies. Like I think it shot some scenes for Wolf in Wall Street. Right? Has anyone seen that movie? Right. So and I think the bird view of the New York City was shot by this helicopters. So we use this equipment to put them above a freeway. Actually, this is just a small section of that freeway. But anyway, so we actually piece together all these um, pictures. We can cover about 1.6 kilometer long, actually about 2 kilometer long segment. So we can actually, just extract the vehicle trajectories, piece these three cameras together to get the long trajectories, about 1.2 miles of trajectories. That shows the complete patterns of the shock wave of propagation and dissipation for bottleneck in Florida, not or along Tampa. And also we have a recent this is for freeway. For Arturos, we flew like 2 drones and covered 2 segments, and we extracted the trajectories. You see stop and go patterns for of these vehicles at the signalized intersections. We're using them to look into the energy impact of current technologies as opposed to the connected automated vehicles. So here, where does AI fit in the scene? So basically, you can use actually AI. Definitely extracting objects. You have to use AI right now. Actually, my undergraduate research was also doing like video recognition, but that time we didn't use AI, so the quality was very bad. Right now, we use AI. We can extract a really high resolution trajectories, and based on that, you can do lots of analysis, right? And this is more about the work zone inspection. Let's say we actually did some of the pilot work with our lab vehicles. So we have a road, this is Madison, we have a road called Whitney Way. It had some construction segment here. So we drove our lab vehicles with a camera and LiDAR sensor to sort of like scan the roadway. And then with that, we bring back the data and fuse the video and LiDAR and doing some recognition. First, we will construct a digital map, right? So that is 3D point cloud plus some video footages. Then we did introduced some AI. Yeah, like this. Oh, I don't know why this doesn't. Sorry about it. So it looks like I don't work very well with. Let me try to use this. See whether this one works. All right. Okay. So I think the file is big. So does it work? Okay. It plays. Okay. Anyway, it's fine if it doesn't play. It shows you the idea. So basically, with the AI, you can actually just doing some object identification. Now, instead of a point cloud, you can segmentize the view, and these are drums, and there is a sign, and there is a beacons, and with this kind of information, you can actually, automatically process if these assets are positioned properly, if there is a problem according to, and that will answer some of the questions from the state DOTs about work zone inspection, right? Okay. All right. Of course, besides work zone, you can also do like the payment inspection. So, these videos don't play well. I don't know. Let's see. Sorry. I think the reaction is like. All right. Now I hope I get there. So, but basically, so I think before AI is widely used, and most of the state DOTs use very expensive vehicles, maybe like $1 million, $2 million a piece, and doing some inspections. But right now, with some of the very cheap sensors, it looks like this is actually recorded by an iPhone. With iPhone, you can extract the payment crash patterns very well, and then you can do use some AI to do segmentation to get the correct patterns. And so this is then the hope is we can use much cheaper technologies to do more frequent inspections of the payment. All right, that will help the state DOTs and transportation agencies much better monitor the highway and payment conditions and make better and more optimized decisions for payment, repair, and maintenance. And also, there is a trend of, so AI is a very commonly used technology, right? So you can apply it to traffic problems. You can also apply it to asset management. You can also apply it to material design, Lots of those different parts of the civil infrastructure life cycles are now brought together by AI, right? So I know traditionally people are divided by the, planning side is this planning? Yeah. So let's see, where is the planning? So anyway, this is a planning and the design side. Planning has a group of people. We don't talk to other people. Design has a group of people. Construction, maybe they talk more with design, but maybe not too much with operations. So in the industry as well as government sectors, these different sectors are pretty much siloed, and we don't talk too much to each other. Think about when was the next time when you talked to a designer, right? That might be a while. All right, but now we have those kind of more powerful AI technologies, and also we have much powerful cyber computational infrastructure like GPU and all these things. We can all lump sum all this data together, really have a comprehensive system, like foundation system for transportation, right? That covers the whole life cycle of the infrastructure. You can integrate GIS with 3D models. Actually, I'm working with my colleague Sky to try to integrate these planning and the design of working with Wisconsin Department of Transportation. Construction DIM can be also incorporated, and operations and management traffic detected data, and also US DOT wanted to incorporate them under the umbrella of the BIM, and with that we hope to have one-stop shop of all this data, and then you can do all this analysis all together, right? So this is a vision we have. Hopefully you guys, I invite all of you to join this effort of break the barriers across different phases and really take advantage of the big data, AI, and computation infrastructures. Digital twin. So we have real-time high-definition sensor data. We integrate with all this sensor data, just like I said, if you integrate a life cycle, you pretty much can have everything done in an integrated platform. All right, so we started from the traffic side. We got some of the video cameras, and we're trying to use our own vehicles as well as available roadside units to construct the digital twin. Again, working with my colleague Sky. And right now we did just a preliminary study. If you get the cameras, this is the real world detection, but we mapped it to more of the computers. So computer graphically generated digital twin that needs to be synchronized with real world, and we can use that to play back to see what happened in the past, and monitor what's happening now, and predict it in the future. And they can have lots of applications like weather detection, accident alert, and many other things. So along the perception direction, I would say there's lots of opportunities and as well as the challenges, right? So what I have done was when I started to work on AI, the easiest thing is just to apply existing AI methods to what we're doing, right? There's already, the computer vision field has developed lots of this, object detection, segmentation, tracking algorithms. We can just directly use them to apply them to the transportation sensors, and this part is easy. The challenge is like, how do we actually, with one vehicle, one camera, that might be easy, but how about we have multiple cameras from the different vehicles or roadside units? How are you going to integrate them together? So cooperative perception would be something that we really want to dive into. And I believe that US DOT is going to issue some call for proposal on this topic. Actually, I had the communications with their officers, and I know they wanted to invest on this direction. And also, they wanted to reconcile historical static and real-time dynamic data in digital twin development. Uh, right now, actually, like I showed, we could use the data to do some static, like infrastructure-related, asset-related analysis. But also, we can use the AI to extract the real-time, road users, right? Vehicles of human, bicyclists, all these things. I think about it, you just create a digital twin system to lump sum all this data together and work them in a new environment. Now you have much higher dimensional, much higher nonlinear problems, and that can benefit from the AIs. And of course, tech transfer products and business models, they're also viable commercialization opportunities in this direction. All right, now I'm going to talk about the evaluation, which is moving further from sensor to automation technology. Sensing is only a part of the automation, right? That's the upstream of automation. But we really want to understand, there are so many, like as I saw many hands raised when I asked whether you had low-level automated vehicles. They're already running up there, just like Professor Huang mentioned, how to evaluate the safety performance of those vehicles, right? It's a challenge, right? And also not just the safety, mobility and energy impact, and also you can think about many criteria of understanding and evaluating these technologies, right? So without objective scientific understanding of those technologies, so how did people understand those technologies? Yes, a lot of times it's driven by the commercial interests, right? Stock market, right? So I just showed one stock market of one, actually I didn't show the name, but this is actually stock market of one AV company, right? You see it gets really high and then gets low these years. So people had hypes before, but then they got pessimistic, right? So really, either this or this, I don't think this is a good understanding about the value of these technologies. And also, one accident could cost the whole industry, right? So we need to think about, speak of safety, all right? In the U.S., 30 to 40 thousand people die in 1 year, and rarely that made national news, right? I mean, there are some reports, but one AV kill could definitely, or not even kill, but injury, right? So the recent cruise had an injury and could make the national news, and everybody is really scared about the new technology. It's like a Terminator or something, right? So, but these are like fake impressions. We need to, as from a research and academic community point of view, we want to provide the public the objective understandings of how these technologies perform along all these dimensions, right? How do we do that, right? So we need to fill the gap to really help people to objective understanding. All right, so I believe first is like we have existing research on AV test. AV test is not a new topic, but lots of these tests right now focus on a component-wise test. Like you heard of NCAP, right? This is testing standard. They were just a test. Okay, adaptive cruise control. All right, automated lane change. All right, automated emergency brake. They just test them one by one. But they and also the issue is actually these autonomous vehicles drive in a complex environment, and their decisions are not segmentized into one. Just like you cannot completely separate them into independent components. It needs to operate in a comprehensive environment, right? And also, as the technology develops from the rule-based to AI-based technology, you guys probably had heard of the Tesla, full self-driving version 12. Maybe it's not open here, but in the U.S. it really made a buzz, and it's like a blockbuster type of show, right? So and I tried the system. It really is different from the original system, but the downside is that black box. It uses probably like lots of AI into it. And how are you going to separate them into different functions? if it's a complete black box, right? We need to have a large amount of data to really conduct a comprehensive test of the vehicles in a realistic driving, complex driving environment, I think, right? So, but it's difficult to do that because we don't have such a good amount of data, and the commercial companies also keep the data as a secret, right? That's their competitive advantage. So it's interesting, right? For those kind of like AVs to be tested, they don't need to share the source code. They don't need to share their logic or data. They just need to pass certain simple tests. But how we're gonna trust that? All right. Sorry. So first, I guess we need to get the data, right? If you have the data, we can do some of the AV analysis. For example, you can use projected level of data to do more comprehensive AV behavior model and do evaluation ranking. I mean, this logic is not so much difficult. It's like when we're doing car follow model, lane change model, or this traffic flow models, we're using this kind of logic, right? Except these are, right now we have bigger data and we need to have bigger model, and we may need to address not only the traffic mobility related issues, but also safety and energy and other aspects, right? If we have good models, we can sort of rank their performance and show, for example, just a tease. It's like just you can have best in U.S. News car rankings or something like that, right? All right, we're not ground zero right now. We actually had created a committee at IEEE ITSS and called Emerging Transportation Technology Testing, and we actually also, I know lots of agencies have collected lots of data on the AV performance, particularly the trajectory data, right? You have so many data sets. We use our community, such as maybe KAIST and also IEEE, all these. We can try to promote the data sharing, and we're working on this area, and we're also just submitted paper to summarize the longitudinal data of all these available data sets, and also we can try to work together to standardize some of the data. Maybe next step would be, it's not going to be just longitudinal, you need to consider the lateral and also complex environment. And then it's not just the trajectory, you may need to get to some of the end-to-end, starting from the sensor going to the steering wheel type of data, right? So once you have this data, you'll be able to, construct a modeling framework. That is where the big model is from, right? Data input. Right now, let's say we have trajectory data, then we can we go through some of the trajectory construction to filter out the noise, and then we create some vehicle behavior models. All right, it can be as simple as car following, but as complex as really the series trees. Even some people try also large language models or foundation models as well. And then there will be some of the testing goals. For example, safety, efficiency, could be energy, right? Then you can generate some scenarios and test them and do simulation and evaluation. I think Professor Huang also alluded to some of the thoughts here. So, we did some of the preliminary studies just to use, I think we used LSTM, which is AI model, more complicated than car following, but less sophisticated than foundation models. But we can, with trajectory data, I think it's good, and we use it, and we actually did some learning to predict it from the past state to the future state, and that is actually how you're going to construct these traffic, like traffic dynamic models or vehicle dynamic models. And then we did some experiment. We have PAV trajectory data from OpenACC data, which is a great set of data collected by our European colleagues, and that has a different variety of vehicles. All right, and then we actually extracted their models. We plugged these models into Sumo and tested some of the scenarios. with sumo model, maybe a prototype digital twin along the UW Madison. And then we can compare their distribution of their performances in terms of this is safety, it could be TTC, and this is fuel consumption, and then this is say let's see, this is like the speed of standard deviations about stability, right? You can have all these different criteria, and you can compare, the distribution of these measures across different vehicle types, right? And then you can have some of the measures really compare them, which one's good and which one's not so good. All right, it's this is just a really preliminary test along this direction, but I think it can. You may have a lot of things to do along this direction. Actually, how do we do lots of tests of existing technologies, and we need to come up with good models to accurately reflect their behaviors, and then we bring them back to some of the complex scenarios to test them, and we hope the tested performance will really reflect their real-world performance on all these aspects. When I say this is just a starting point, is because not everything starts from trajectory. Okay, maybe in the past, because of lack of data, we were playing with density and flow. Right now we have some trajectory data, but in the future I think you need to realize the end-to-end pattern. All right, so vehicles that are dealing with this kind of camera data, right, or some with radar data, right? They need to recognize that traffic signs, traffic lights, traffic signs, right, in different conditions, and also road markings. We actually work with Florida Department of Transportation. We're still working with them to look into how different vehicles will be able to recognize these road assets, road signs, road markers, or what is their sensing capability of these? What are the sensing capability of these vehicles, and what's the difference between different vehicle types? And based on that, first we understand how our existing infrastructure is well prepared for the existing automakers, and if there are gaps from the infrastructure perspective, what do we need to improve? And from the perspective of automakers, what do they need to improve to? Basically, it's like two-way. Actually, automakers need to do some things more compatible with the existing infrastructure, and the infrastructure also need to improve them to say, to be more forgiving, right, just I'm actually citing a word that Professor Huang said. We need to be a forgiving highway system to not only human beings as well as to autonomous vehicles as well. All right, so with these data, next step we need to have really complex open scenarios. And also another thing is I really urge all of you to do is we need to have some benchmark data sets and benchmark problems. All right. This is a big problem in our field. Okay, so I feel like over these 20 years, so people are all working on the same field. You ask them, okay, what are you working on? Connected automated vehicles, whatever. But there is not that much standard benchmark problems data set. The very basic question is very difficult to answer. In this area, whose work is the best? There's no comparison. Everybody is the best, right, from certain measure. But I think if you look around in other engineering fields like computer science, some of their boosts was largely based on the benchmark data set and benchmark problems, right? For example, video-based computer vision, all right, who can recognize this picture the most accurate will win the game, right? So I think with all these data sets, we hope to create some of the benchmark data set and also benchmark problems so that we can just converge our focus on some valuable problems and save our energies from some of the distracting points to really push this field forward. Otherwise, we have a chance of running behind of the game against some of the other field, because computer science people they're also working on this, and of course we're all in this community. We need to benefit from all these different areas, but one way to benefit from all this interdisciplinary expertise is to come up with some converged topics and benchmark problems, benchmark data set. All right, so with this benchmark data, you'll be able to do lots of things, like you're going to create benchmark data. If they are really complex enough and really have lots of reasonings associated with them, you can do like big, large models, including foundation models, right? Benefit from those, generative foundation models, and then you can have extract all these impacts for example, let's say my dream is actually, if you collect the sufficient data and from certain vehicles, before these vehicles even get to the road, you can predict it accurately how they perform in Jeju Island. Like, if they keep running at the Jeju Island, what is the incident rate? What is crash level? What is the energy consumption, right? What kind of traffic capacity you're going to have to answer this kind of questions, right? All right, so last I hope I'm not running over the time, but I want to talk about a cooperation, which is, maybe automation, you can say that, but cooperation is something that is lacking, actually. I think this vision has been there a while, this cooperative driving automation, right? If all the vehicles are cooperating, if you look at the signalized intersections, this is time and this space, let's say, vehicles driving this way and the signalized intersections, green, red, alternating, and this pattern. If all these vehicles are coordinated, they don't need to get to there and make a stop. They just need to glide through the signalized intersection at the right time window. This is going to yield a highest capacity, right? It's going to reduce the rear end collision because the speed difference is minimized. And also the energy consumption is minimized. Right, this is a vision, but it's not easy to get there because we need to have participation of the infrastructure and automakers. When automakers making the vehicles, they don't need to prepare for that, right? So we actually did some tests of how well they can follow prescribed trajectories. Like I said, this is a prescribed speed profile of the target, and these are their profiles of different runs actually with different settings. They're quite drastically apart, right? If you use that technologies to this application scenario, vehicles going to crash into each other, all right? So, we need to have better control, all right? If you won't do that, then how do we improve the control? We try to, I think lots of this control is based on like sometimes reactive and PID control actually also, or some of the classic control. But really we need to think about model predictive control plus some learning, actually integrate them together, and we did some tests with really shabby small scale vehicles here, right? They're difficult to control if you play with them, all right? Difficult to put down, to let them follow the prescribed trajectories. Doesn't play well for every video. All right, I hope. Let me see whether the video plays. Oh, well, no, maybe. All right, we did some tests, and especially for platooning formation, platoon splitting, and actually we combined these vehicle. We did some of these tests. Actually, it's not a complicated problems, but we compared to the PID control as well as the MPC plus online learning. We see that using this new technique will much reduce the error between the controlled trajectories and the target trajectory. All right, 70% of improvement for this simple example. That's one. So we need to improve the control. And another thing is, right, when vehicles drive, for a foreseeable future, maybe if there are AVs, and in most of the scenarios, they're going to share the rights of way with human drivers. Human drivers are unpredictable. But how do we, consider properly address interactions with human drivers and devise the proper AV controls? All right, so to achieve the vision of eco driving is also an interesting thing. And also another thing is, let's say, let's think about the criticize the existing traffic flow models, right? for existing traffic flow models, actually, they're simple. They can shed the insights variable, the first order insights variable. But if you're, you really need to scrutinize the problem at the level of control. The issue is they may not be able to well predict each individual vehicle's behavior due to the, they cannot capture heterogeneous microscopic behavior, and it's a system's nonlinearity and hidden players are not well captured, right? And therefore the AV control based on like the predictions of the classic traffic flow models of human drivers may not be that successful due to the inaccurate HV prediction. And therefore, we actually worked with, like UW colleagues, including Professor Skychen, to come up with a framework. We call it physics enhanced residual learning. We basically want to enhance the physics prediction with the learning to improve the residue. That is, we learn the difference between the true value and the physics value, that is a residue, and we add that to improve the prediction. And we have very good results, actually. We compare the prediction errors of the Pearl, which is our physics and enhanced residual learning, with some other neural network and physics-informed neural network and the physics models alone. We see when data is small, actually, our Pearl predicts the target trajectory much more accurate than other methods. And as the data gets improves, actually our Pearl model still performs the best. But although their difference is not that much dramatic, because you give enough data, the neural network can learn the very detailed the very detailed patterns of the trajectories and make the very accurate predictions. So when the data is sufficient, their difference is not that much. But I want to say, actually, our model is much smaller and takes much less time to converge to this quality compared to other models. All right. So this is a promising direction. And of course, besides modeling, you need to do the field developments, right? Field experiments. Actually, this is one experiment we did. So many years ago, in collaboration with some visitors from China University, and actually. So this is a signalized intersection, and there is one signal that's in turn from red to green, and this is the CAV, and these other vehicles are just human-driven vehicles. So when the system starts, all right, these vehicles the human-driven vehicles will stop here, but this CAV knows when it's going to turn green. We'll just join the queue at the right time without fully stopped, right? We also conducted some study with for multiple intersections at light traffic, working with Argonne National Lab. You see, actually, this is the vehicle trajectories. They can glide the vehicle through the intersection at the right time without making a stop. Of course, this is light traffic, and we're in the process of doing more, on track, closed track tests with mixed human drivers, real human driver vehicles, and we have been also discussing with the Wisconsin Department of Transportation and the City of Madison in hope of testing some of these technologies in public road with heavy traffic. So along this direction, there will be lots of research opportunities and challenges as well, and field experiment with accurate control and consider multiple complex conditions, and also really demonstrate that in the real world, and to show the companies that there is a really savings and benefit, and that's going to offset the cost and energy and other overhead they have. Then this technology can run. All right, I'll just stop here. I just meant to bring up some of the topics in this space and let you. Really, I want to discuss with you and learn from each other about how we can jointly improve this research direction and expand our horizon. Thanks a lot.
Okay, any questions or comment from the board?
when you do the cyber-physical environment, the collaborative perception, and each entity has different operation units. So do you have any idea how you can combine them all together? Because each has different authority and operation unit, so it's very difficult to combine them together.
Right. So, yeah, there are two ways. One is a fleet vehicle, right? I've seen some successful deployment in, for example, state of Utah, where signal priority and emergency vehicle priorities are good manifestation of the connected vehicle technologies. You just work on the vehicles under authority in a fleet that is controlled by one unified authority, right? That's one way to do that, fleet of vehicles. The other way is companies are doing that, right? So like Tesla, they have all these vehicles. They can access the data, right? They can update the control. The video that I showed is already what they're doing. They're already combining the information from the different vehicles. So I think the companies may be able to do that. And if the company collectively bargain the shared, for example, traffic signal, like connected vehicle input, that might be a viable way to do that. All right, and it's really going to be difficult for different companies and all these private vehicles to work together to have that centralized control. Maybe that'll take quite a while, but before that, I think there are still quite some use cases with fleet vehicles and vehicles owned by the single company. Thanks.
So, any other? Yep.
Yeah, thank you for the presentation. I like the idea about having a benchmark and everyone can use the same data sets and maybe we can compete each other. But at the same time, when I put in some papers, regarding this, some reviewers say it's not that important, whether your performance, your algorithm performs better than any others, as long as you can explain why it happens. So it should be some explainable when you're doing an algorithm, particularly when you're doing some deep learning or neural network stuff. What do you think of it? Do you think it's still it's a worthwhile we compete with same data set, but we can show off my algorithm is better than yours?
Yes, I think right. I understand that parsimonious models and also some explainable format, the elegant analytics have been holy grails in our field. I've been working on analytics a lot, and I can write those closed format, equations and proofs. Right? I published a paper even recently that been called proofs. So I think it's beautiful. It's good to explain them, but really, we need to understand what the problem is. Whether the problem is understand the system or we want to do something more than just understanding the system. If we're just evaluating if we just want to get the physical insights, right? So that's the objective of your study when you do it. But in many other cases, okay, the objective is just, for example, saving lives. If you have one algorithm, put it to the autonomous vehicles, that's going to have much less crashes compared to another model that is explainable. I'd rather go with the first one, right? I think that depends on what you want to do. And also think about it, human brains, we process, do we have like an analytical model in our brain? No, we don't. We're doing things sometimes not that explainable. And it succeeded, and it works pretty well. So I think number one is for lots of applications, we need to get the job done best. And on top of that, if we can explain it very well. If we cannot explain it, I think I would rather like to sort of trade some explainability for some better outcomes. Really, but of course, we need to understand this AI's performance holistically. It has safety risks, it has ethics issues, but there will be ways of understanding them. There are statistics, right? There are some of the verification models and other ways of doing that. It doesn't necessarily need us to come up with a simple model, but we need to have smarter ways of dealing complex problems and really give us correct answers. All right, so basically to summarize, for problems that you just want to explain the problems, look into the relationships of the key factors. I would really cherish the explanatory models and the low order models. But really, if you want to solve some other problems, that is just performance based on, or just to go with that.
Okay. Oh yeah, go ahead.
I have an interesting question. Nowadays, more and more sensors are integrated on the autonomous vehicle. However, the CEO of Tesla, Elon Musk, believes that the system should be based on the human driver. They only use camera and neural network, just like humans use eyes and their brains. So how do you think of that?
Yeah, that's a really interesting question. You're right about your question. Interesting. So yeah, I actually showed that their debate to the class. Actually, I know Tesla, Elon Musk is pretty harsh on LiDAR right now. So I think I don't have a crystal ball, and I don't know what the future would be like. And the questions we need to evaluate them both. Actually, that goes to the evaluation. If you have vehicles that has LiDAR compared with vehicles that does not have LiDAR, do we have a way to answer your question? Actually, doing some tests and to show you this is which vehicle is gonna work better in what kind of conditions, right? We don't have it. Congratulations, we have new research opportunity. We might need to develop new research instruments for doing that, right? We need to have a test track, or you can take advantage of your dyno, make that as a VR for those vehicles to do some of these tests, right? And I've also been very interested in really having some good systems and ways of doing holistic tests of these vehicles, and then we can answer that, right? So I have some personal thought about these technologies, but I'm not going to share that with you as a rigorous researcher. I don't want to bet on one over the other, right? Yeah, if you want to know my personal view, we can have a dinner together. Yeah, all right, sure.
Okay, so any more questions or comments? Okay, then, well, let me take advantage just 1 minute or 2 minutes because I have a question. So actually I'm doing some project with the test field and then developing test scenarios. Well, every time I'm thinking about the test scenarios, I'm thinking about, so how many scenarios we need to go through for the automated vehicles to go outside so that we can be sure like that so this automated vehicle guy can go outside and can interact with the other people or with the other road object. So how many scenarios, or maybe how dangerous scenarios? So what is the criteria to be sure that the automated vehicles can go outside?
Now, I cannot answer the question, but I can try to provide a solution to get a way to answer your question. All right. So how do we find an answer to his question? Okay. So basically, you need just enough number of scenarios and diversities to make sure that your evaluation is consistent with their real-world performance in certain operational domain. That is like a golden answer, right? So that's never wrong. But how do we get there? All right. So we need to have enough data. That is the bottleneck, right? So, let's think about in the past. Do we have enough data for existing vehicles' performance in the real world that you know? Did we track these existing vehicles' performance, like across safety and other things? Let's say in Jeju Island, all right. Let's say a Honda vehicle, particular model. What is their performance? First, if you have that data, all right, come back, use your method to try to see how many scenarios test will get your prediction results close to the real world test. All right, that is verified by several different models of vehicles and even some of the autonomous vehicles, and that will be a reliable method to answer that. So basically, it's a statistical question, so we answer them with the data. And also that's why we need to share the data, and we need to have the sufficient data samples to really measure whether your research predictions is close to the real world performance. Thanks.
Okay. Yeah. So any more questions or comments? Then, well, let's just give him a big hand.
Thank you.